course of today. So now we'll have the first talk by Roland Bauerschmidt, who's going to give us a course about Log-Sobolev inequalities and renormalization. So where are you actually physically right now, Roland?
I'm physically temporarily in Germany.
Okay. So Roland from Cambridge, but right now from Germany is going to. So please go ahead.
Okay, well, thank you for the introduction, and also I'd like to thank the organizers for the great opportunity to be part of this summer school. So what I'll be talking about is mostly all contained in a paper which is joined with Thierry Boudinot, and I guess it's linked on the summer school's website. So what I'll be discussing is stochastic dynamics of the simplest kind. So we have what I call a field phi, which depends on time, and it just evolves according to this d phi is given by minus gradient h phi t dt plus noise. And for essentially all I'm saying, I'll be assuming that phi is just an Rn. And n is some large finite number. Usually I'd like to identify Rn with a large number of points. So I'll be thinking of say the set 1 through n as indexing a large number of points, and in fact, in the cases we'll be interested in, these numbers of these points will approximate, let's say, R2 or Z2, or more generally ZD. Okay, so this evolution, as most of you will very well know, has invariant measure given by e to the minus h, and I will denote this by nu infinity. So the invariant measure is proportional to e to the minus h of phi d phi just being the Lebesgue measure on Rn. And so up to now, the structure is extremely general, but the cases we'll really be interested in those cases, H has a much more specific structure, and it's given by one contribution, which I'll denote by A phi t. And A is in this context just an n by n symmetric matrix, which you should think of as a Laplacian. And then there's a local potential, V prime, or maybe I should write a gradient V of phi t. And this V is local. So really, so A you should think of as Laplacian on lambda, which will approximate, let's say, RD or ZD, and V is a local potential, and it will be nonlinear. That would be the whole point. Okay, and so I'll be calling this continuous Glauber dynamics. It's local dynamics, local stochastic dynamics without any conserved quantities. So this is what continuous Glauber dynamics is, but especially in the general context, where for general H, this is also called Langevin or Glauber-Langevin dynamics, and a whole bunch of other names, but this is what I'll be calling it. And let me give you a couple of examples of what kind of systems we have in mind. So basically, so recall that h of phi is consists of two parts. So there's the quadratic part, and then there is the potential part. And choices to have in mind are, on the one hand, lattice models. So this is, roughly speaking, the kind of setup that Hugo was talking about. So in this case, I'd like to take A to be, let's say, minus the Laplacian on a set lambda, where lambda is maybe a subset of ZD. And and this lattice Laplacian is defined by summing over the neighbors of x and then taking f of y minus f of x. And the potential could be, so one popular choice, which is the one that Hugo already discussed, would be the phi-4 choice. You sum over all lattice points, and then you have the potential, which is consists of one term g phi to the 4, another term nu phi squared. And the case of g of interest, g is positive and nu is negative. So this is a double well potential. Another choice, which is closer to what I'll actually be talking about, is would be a periodic potential. Again, so you see these potentials are sums over all lattice points valued at the same point x, so they're local. And so the periodic choice would be, say, some constant, the z cosine, some other constant, which is conventionally denoted square root beta phi. I guess I don't need this. And so here z is a real constant, a real valued constant, and beta is positive. And this would be the lattice phi-4 model or the lattice sine-Gordon model. So in this notation up here, I haven't actually told you what that bracket means, and it's would be inner product appropriate to the setup. So in this case, the appropriate inner product is just the standard Euclidean inner product. Okay, so these are lattice models. Another setting would be continuum models. So in this, this is the case where the dynamics will converge to an SPDE. So here A is again a Laplacian, but in this case it's a continuum Laplacian, or what I will take is a lattice regularized continuum Laplacian. I'll explain carefully in just a second. And sometimes also useful to add a constant term in this setting. I'll also explain in a second. So let me first say what this Laplacian is. So here we're looking at, instead of a subset of ZD, I'm looking at a set which I may denote omega epsilon, which is maybe epsilon times, so the lattice of spacing epsilon intersected with some, let's say, bounded or unbounded subset of RD. And the Laplacian epsilon f of x is defined as in the lattice case, except that I normalize it as is appropriate of thinking of the lattice as a lattice of mesh epsilon rather than of mesh 1. In this case, the natural inner product associated would be the one that is normalized with respect to the lattice as well. So it would be, say, inner product epsilon, maybe here is inner product lambda. And again, you can consider models similar to their lattice versions. This would be the continuum phi-4 model for the first case. So I'm looking at So important point that's missing. So one difference is I'd be normalizing sums with respect to the lattice width, so that this sum looks like an integral, just as I did in the inner product. Then you can define the continuum phi-4 model, which is defined as the lattice version, with one important, very important difference, which is that the coupling constant, in this case of the quadratic term, needs to be made epsilon dependent to get a non-trivial measure as epsilon tends to 0. So maybe, okay, let me write down the continuum sine-Gordon example as well, and then explain a little bit what the conceptual difference between these two classes of models, the lattice models and the continuum models, are. So again, in the continuum sine-Gordon model, I'm looking at a sum normalized as like an integral, and then again, I need a divergent constant here, which in this case is epsilon to the minus beta over 4 pi. So this case is d is equal to 2. And we have cosine square root beta phi. Okay, so okay, let's look at these models I've defined. On the one hand, we have the lattice models. So these are sort of the models whose interpretation comes from statistical mechanics. We have a unit lattice. At every point of the unit lattice, we have a spin phi x. Those spins interact through one of these potentials, which are nonlinear functions of local functions of the field. In the simplest case is given here would be this square well potential, the phi-4 model, or periodic potential in the sine-Gordon case. And the interesting questions here are, what is the large scale behavior? What happens if the set lambda tends to infinity, becomes all of ZD? And what can we say about these models, especially as a function of the parameters that go into the definition of these models as the system size becomes extremely large? And so you saw a few examples of such behavior already in Hugo's talk. Typically, there's going to be a critical point. So for the phi-4 model, if you're very new, with G fixed, the behavior will change drastically at a certain critical point, etc. And the story is similar for the lattice sine-Gordon model. And the continuum models, on the other hand, those models, the point of view is a little bit different. We fix a continuum set, omega, and then approximate it by a fine lattice. And then what we try to do is we try to choose a potential. And so here the potential depends on these so-called counter terms. In such a way as to obtain a non-Gaussian measure as epsilon goes to 0. So in this setting, one usually keeps the volume finite because you already get infinitely many points by taking epsilon to 0. On the other hand, in the lattice models, you take the lattice to infinity. So now, as is completely apparent from what I've written, is that you can translate one model into the other, of course. You can take the continuum model, rescale everything by epsilon, and then you basically have a lattice model. There's a subtlety, though. You can, of course, do this scaling, and if you do this scaling at the level of the Gaussian measure, those points of views are completely equivalent. But if you do this rescaling in the presence of nonlinearities, it's very different. Because the rescaling of the field enters how the coupling constant change. So if you look at, if you try to do this rescaling, say in the phi-4 model, you see the coupling constant has an epsilon to the d in front of it, in front of the sum over all lattice points. Here you have a coupling constant of order 1. So while these models are close, these classes of models are closely related, many things are quite quite a bit different. So anyway, so these are the kind of models I have in mind and I want to discuss. And what we want to discuss is what we can understand about the let's say the long time behavior of the Glauber dynamics associated to these models. So before doing this, let me discuss a few generalities on this kind of stochastic dynamics. Many of you will know this very well, but it's important for what's to come later. So I'm looking at this diffusion dynamics, and I've already mentioned that there is an invariant measure associated to it, and there's also an infinitesimal generator. Sorry. So the infinitesimal generator is, I will denote this by Laplacian H. It's given by Laplacian minus gradient H inner product gradient, or written in a different way, e to the plus H gradient e to the minus H gradient with an inner product there. So at this point, I should emphasize that this Laplacian is not at all the Laplacian that we saw on the previous slide. So this Laplacian was a lattice Laplacian, or was a Laplacian on this physical state space. This Laplacian that appears in the infinitesimal generator is a Laplacian on R to the field space. So it's a Laplacian Rn rather than n. So here we sum over all x and lambda. And then we take d phi x squared. Similarly, this inner product is the sum over all x and lambda of dh d phi x d phi x. Good. So then we have the invariant measure, nu infinity, and nu infinity is reversible with respect to this dynamics. And in terms of the generator, what it means is that we have the following integration by parts relation. We take two functions, f and g. F and g are functions on Rn. And if we look at the expectation of f minus Laplacian g, that is the same as the expectation of the inner product of the gradients of f and g. Also, by Ito's formula, if we define ft of phi as the expectation with initial condition phi naught is equal to phi of f of phi t, then this this function as a function of t solves of t and phi solves the linear equation ddt ft is Laplacian h ft. Okay, so often, so this is the point of view of the evolution of the field. What we'll be interested in really how the law of phi t looks like. So so the law of phi t, so that's the distribution of phi t. So you start with some condition phi naught, and then you run the dynamics up to time t. So that defines a probability measure on Rn, and it's just defined as follows: the nu t. The expectation of some function f with respect to nu t is the same as the expectation with respect to the original measure nu naught of f evolved to time t according to the above equation. And then you can also write down an equation for the law if you like. So one that will be particularly convenient for us is that if you write the law d nu t as some function ft times the invariant law, so nu is f times nu infinity, then ft satisfies, well, by definition, sort of, the equation that df dt is given by the adjoint of the generator applied to f. So here, this adjoint of the generator is the adjoint with respect to the invariant measure nu infinity. But since this operator is symmetric with respect to the invariant measure, this is just the same as Laplacian h ft. So somehow the law with respect to the invariant one, or the f which describes the law with respect to the invariant one, satisfies the same equation as the observable. Good. And you can also, if you like, write down an equation that the law itself formally satisfies, the so-called Fokker-Planck equation, but I'm not going to do that because we won't need it. Okay, so these are some generalities on these kinds of Markov processes. And so then under very soft conditions, these processes, remember we have a finite state space, and under very soft conditions, roughly equivalent to the condition that equivalent for a finite state Markov chain, that the state space is connected. These Markov processes are ergodic, and that implies that nu t converges to nu infinity. And the basic question we're interested in is, how fast does this happen? In particular, how fast does it? How does this rate depend on the parameters of the model, the size of the state space, so the dimension, the epsilons, and so on? Okay, so and now there's various ways to measure this. We need some kind of distance to compare nu t with respect to nu infinity. And there's different choices you can make, but one that has proven to be an extremely good and useful way to do that is the relative entropy. So the relative entropy between two measures is nu t and nu infinity, is defined as follows. It's I write it as nu infinity of f log f, where f is the Radon-Nikodym derivative of nu t with respect to nu infinity, assuming this exists. Otherwise, the relative entropy is infinite. And so that's the relative entropy. And often this is also written as entropy with respect to nu infinity of f. But the good way to think about it is it's the relative entropy of the measure nu t with respect to nu infinity. Okay, so there's some basic properties of, okay, so relative entropy is a good notion because it has a lot of good properties, and I'm not going to go through them right now, but you'll see some of them as we go. Let me just mention in passing that that it's a strong no, it's not a distance, it's not symmetric in its two arguments, but it does control the total variation norm. So if you take the total variation norm of nu t and nu infinity, this is bounded by in square by 2 times the relative entropy. Okay. So one of the properties that makes the relative entropy so useful is that we can that there's a formula for how it changes as we run the dynamics. So this formula is expressed in terms of the Dirichlet form of the square root of the function, which is as an information theoretic interpretation is called the Fisher information. That interpretation is irrelevant for us, but this name is standard, so I'm going to use it. So it's denoted I of nu t with respect to nu infinity, and it's defined as the expectation with respect to the measure nu infinity of square root of the gradient, the gradient of f squared divided by f. That's the so-called Fisher information, and there is another way you can write the same expression, which is as the gradient of the square root of f squared. And you can, you can see that both of these expressions are the same, because if you differentiate the square root, well, that gives you a gradient f divided by a square root of gradient f, and you have two of them, so you get the 1 over f. Okay, so that's the so-called Fisher information, and as I already mentioned, there is a one of the useful properties one of the many useful properties of the relative entropy is that it has an explicit formula, and that its rate of change is given exactly by the Fisher information. So this is sometimes called the Brewing Identity, and it just states that if you take the time derivative of the relative entropy of nu t with respect to nu infinity, this is minus the relative Fisher information of nu t nu infinity. And in particular, it's negative, because as you can see from the definition of the Fisher information is positive. So the derivative of the relative entropy at time t is negative. So the relative entropy decreases. Let's, because it's nice and instructive, let me just check this de Bruijn identity. So maybe I'll move this to a new slide. So let's just check it. So what do we do is where we want to take the derivative of the relative entropy, and I'm going to write it like this. I'm going to write it as expectation of phi of ft, where this function phi is x log x. So phi of x is x log x. Okay, so that's the derivative. So that's the left-hand side, and so we just differentiate it. And well, what do we get? We get this is phi prime of ft times ft dot. So this dot will always denote a time derivative for me. So we substitute in what the time derivative is. That is, as we saw, the generator applied to ft. Now we can use the integration by parts formula. Integration by parts formula brings out a minus, and what we get is gradient phi prime of ft, gradient ft. Now we simplify this first expression by noticing that, well, phi prime of x is just log x plus 1. Once we take the gradient, the 1 doesn't matter, so it's just the gradient of log x. And you can see that this formula can also be arranged as and so that is the identity. Good. And okay, so we see that the change of the relative entropy is explicitly given in terms of this so-called Fisher information, and the upshot of this is that so the upshot is that if we want to show that the relative entropy converges to 0 exponentially, let's say at some rate, which I'm going to call 2 gamma. The 2 is conventional. So I want to show that the entropy decays like this. This is in fact equivalent to saying that the derivative of the relative entropy is bounded by minus 2 gamma times the relative entropy at time t. And since I've just told you that this derivative of the relative entropy is given by minus the Fisher information, this inequality is can also be written as I nu t is greater than 2 gamma relative entropy of nu t and nu infinity. And so this inequality is the Log-Sobolev inequality. So maybe let me just write it down again a little bit differently. So I could write it as the entropy of F with respect to nu infinity. So this is what I also denoted as relative entropy of nu with respect to nu infinity if nu is F nu infinity is bounded by 2 over gamma times the expectation of the gradient of the square root of F squared. And this we saw is 1/4 times that Fisher information. Okay, so this is the Log-Sobolev inequality, and what the rest of my lectures are going to be about is how do we get a handle on this constant? So that constant gamma here, the Log-Sobolev constant, the one that that controls how fast the dynamics relaxes to equilibrium, in the sense that how fast the relative entropy of the time t law relaxes to its equilibrium measure. Okay, so so this is what these lectures are going to be about, and let me just mention that maybe I can leave this as an exercise, which is that, so maybe I'll also abbreviate the Log-Sobolev inequality as LSI sometimes. That the Log-Sobolev inequality implies what is called a spectral gap inequality, which is another way you could measure how fast the time t law relaxes to its equilibrium distribution. And that spectral gap inequality would be to say that the variance with respect to the invariant law of some observable f is bounded by 1 over some possibly different constant, which I'll also denote by gamma here, times the Dirichlet form squared, the Dirichlet form. So you can check that if you have the Log-Sobolev inequality with some constant gamma here, and in particular with that 2 there, then you get this spectral gap inequality as a consequence. But the Log-Sobolev inequality implies more. I'm not going to be discussing this very much during these lectures. There's in fact, there's many beautiful textbook references that discuss all of the general consequences of the Log-Sobolev inequality, which is Gaussian concentration estimates and many other things. Maybe I'll put up some links on the summer school's website later on for anyone who's interested in that. But for us, this is the way we want to think about the relaxation of this dynamics to equilibrium. Okay, so I've defined for you what the Log-Sobolev constant is. So how do we get any handle on this gamma? Now there's a very beautiful and very well-known criterion for this, which is the so-called Bactriamri Theorem, and it states the following. Where we have a measure so nu infinity as before is a measure of type e to the minus h phi d phi. And the condition of the Bactriamri theorem is that the Hessian of h, so that's the matrix of second derivatives, is strictly bounded below by some constant, say lambda times the identity, and lambda is positive. If you have this, it implies the Log-Sobolev inequality with constant gamma bounded below by lambda. Okay, so that's the Bactriamri theorem, and let's quickly prove it. The proof is very short, actually. In fact, there are many proofs of this result by now, but this is roughly how it goes. So we're interested in measuring the relative entropy of some measure nu naught with respect to nu infinity, right? So the Log-Sobolev inequality would be to say that this relative entropy is bounded by a constant, which is 1 over the Log-Sobolev constant times the relative Fisher information of nu naught with respect to nu infinity. So we know how h of nu t with changes we know how to compute the derivative of h of nu t relative to nu infinity. All right, so this is the integral from 0 to infinity of ddt of h of nu t with respect to nu infinity. So here I'm actually using something which is using that the qualitative fact that the relative entropy actually does tend to 0 as t tends to infinity, which is implied by the ergodicity, which I mentioned earlier. So now we can write the right-hand side in terms of the Brewing identity. So this is, so in fact, there's a minus here. So this is the same as the integral over the relative Fisher information. And we would be able to conclude the Log-Sobolev inequality, which is the following inequality. If we knew that the relative Fisher information decays exponentially as follows. So if we knew this decay of this relative Fisher information, then we could just integrate this bound and get the Fisher information at time 0 here, and this is the Log-Sobolev inequality. So the proof is reduced to checking this inequality for the relative Fisher information. And how do you do that? Well, you do that by just differentiating again. So what do we want to do? We want to take the time derivative of nu t with respect to nu infinity, or written out a little bit more explicitly, of the expectation with respect to nu infinity of gradient ft squared over ft. Now, I'm telling you that the result of this, so this is a computation that I'll assign to you as a homework exercise. it's you see you have all ingredients you need to do this computation. You know what the derivative of ft is, because the derivative of ft is just the generator applied to f, right? So this is all you need to know to evaluate this this derivative here. And what the result is the following. It's a little bit of a tedious exercise, but it's very rewarding because you get a lot of terms, and it looks a little bit hopeless at some point, and then you see how all the terms recombine in a sort of miraculous way to get the following formula. So I need a little bit more space here. Okay, so this is what I claim the result of that exercise is. So this is a completely elementary, but admittedly tedious exercise. And the result is this. Okay, so what do we observe at this point? Well, we observe that that we have two terms. The first term is by definition positive, because, well, f is the density of a probability measure, so it's non-negative, and so here we have the norm squared, which is also non-negative. So the first term is non-negative. We also know that the Hessian is bounded as a quadratic form by lambda times the identity. That was exactly our assumption. So we can replace the Hessian of h here by this lambda times the identity. And then what we have is just the inner product of the gradient of log f, and we can get rid of the log by writing the gradient of log f as the gradient of f divided by f. And so we see this is just equal to minus 2 lambda times the expectation of nu infinity of gradient of f squared divided by ft. And that is exactly what we wanted to prove, right? This is minus 2 lambda times the relative Fisher information of nu t with respect to nu infinity. So I can see there's a greater than, there is, right. This should be smaller than. Good. Thank you. I guess at this point it's equal. Okay, good. So we have checked this inequality for the relative Fisher information, and thus we've completed the proof of the Bactriamri theorem, which states that if you have a measure e to the minus h with h strictly convex, then the Log-Sobolev inequality holds with a Log-Sobolev constant bounded below by that bound on the Hessian. So this is a very nice theorem. It's very easy to state and to check. For us, it unfortunately comes with one caveat, which is that the measures we're interested in, typically in statistical mechanics, they're not convex. And so let me re-summarize at this point. Well, the remaining part of these lectures is how can we do anything without convexity? Is the measures we're interested in are just not. And okay, so is this a good time to take a break, or do you?
Yes, I was just about to say so. So it's
Okay,
probably
so
good.
Let's take a break now. I'll briefly, in a couple of minutes, go through what we did and before the break, after the break, and then I'll continue with the new material. Okay.
Okay, so before I go into the break, there are some questions from from the audience to
So
Roland.
yeah, so here there is one question about uniform convexity as something I should have emphasized. This constant lambda is independent of phi. So this is uniform in phi. So that's important. So there's another question. Does it still work if lambda is equal to 0? Well, if you look at this bound, you still have the first term, but you don't get this quantitative bound. I mean, I suppose it's probably still enough to get. Okay, I'm not sure. It's not the route we'll be pursuing, but you do. I think you do get something if without strict convexity, but it's not what we want to do. I mean, we're really interested in the case which is where it's non-convex, and you'll see in a after the break that okay, you'll see more after the break.
Then we resume at 10 a.m. according to my clock. So what?
So I guess that would be
2 in the UK.
Sorry?
2 in the UK. I think 3 in Germany.
Perfect.
Yeah. Okay. Good.
Very good. So we resume in 30 minutes.
Okay. Great. The conservative case is much harder in the sense that I mean, once you go to the non-convex case, okay, maybe I will explain after the break that there are some cheap ways how you can get from, if you have a product measure, how you can get from the Bactriamri argument or other arguments to something more general, and these cheap arguments they don't work as nicely in the conservative case.
Okay, so shall we resume?
Okay. Okay, so all right, let me briefly summarize what we've done so far. We're looking at stochastic dynamics in finitely many dimensions, n dimensions, but with thinking of eventually taking the dimensions large. And we have this standard diffusion equation here, d phi minus gradient h dt plus noise.
So, and, Roland,
yes.
Did you forget to share your screen, or is it just me that I'm not seeing it?
Right, it should be shared, but let me see. Oh, you. Okay, let me see. Here we go. Okay.
Okay. Very good.
All right. So, okay, I was just re-summarizing what we studied. So we're studying this stochastic dynamics specified in terms of some Hamiltonian or action H, and given in this form. Specifically, we'll be interested in models which are much more specific than being described in terms of a general H, in the sense that they have a quadratic term, which we understand very well, and a nonlinear but local potential, V. Then I explained a few general properties of this kind of stochastic dynamics, how the infinitesimal generator plays in, how the law of the field evolves, and so on. And then finally, we discussed the Bactriamri argument, which is I guess here, which is a criterion for the Log-Sobolev inequality in terms of the convexity of the Hamiltonian. And okay, and then we also saw previously that this implies that in relative entropy sense, the dynamics relaxes exponentially fast to its invariant state. Now I want to highlight one aspect of this Bactriamri argument. I mean, went very fast, but I think it's conceptually very clever. So let me summarize on a higher level a little bit of roughly what happens, where we're interested in how some initial measure nu naught converges to to the invariant measure nu infinity. And we do that by looking at the relative entropy at time t. And we saw that the derivative of this relative entropy can be computed explicitly. And we saw that if we can bound that derivative in terms of the relative entropy itself, that's the Log-Sobolev inequality, then we're in business, because then we get a rate for how this relative entropy decays to zero. Now, how did we get this bound on the derivative of the relative entropy, so the Log-Sobolev inequality? Well, we differentiated, or Bactriamri differentiated again. And this time, so sort of we start not at time zero, but effectively we start at time t, and then we interpolate once again using the same dynamics, and we get a bound how the relative Fisher information relaxes to zero. So somehow the method uses the original dynamics we're interested in studying, this Glauber dynamics, several times, in the sense that first it is what we want to study, and then it also appears again as a tool to interpolate inside the proof. So it relies sort of on local and time contractiveness of this dynamics. It's sort of for every time sort of the distance contracts in a uniform way. Okay, so I'll get back to this slide later on, because later on I'll explain how we want to do things differently. Before that, I think, mention a few main cultural remarks. Many of you will know, but let me just mention a few properties of the Log-Sobolev inequality, which if you haven't seen these, explain to a certain extent why it's a good, why the Log-Sobolev inequality and the relative entropy are good quantities to look at. So the first is the so-called tensorization property, which is that if you have two measures, nu and nu, say, if both of them satisfy Log-Sobolev inequalities with the same constant gamma, or the minimum of the two constants, if you like, then the product measure also satisfies the Log-Sobolev inequality with the same constant. So for product measures, the Log-Sobolev constant is uniform in dimension. Okay, so this is one of its useful properties. Another one is the so-called Hurley-Struck perturbation theorem. Which extends greatly the class of measures for which one can establish the Log-Sobolev inequality, and it says the following. So all of these are very easy to establish. They basically just plug in the definitions and check. So if nu satisfies the Log-Sobolev inequality with a constant gamma. And we have another measure mu, whose relative density with respect to nu is given by some function which I'll call f. Then mu also satisfies the Log-Sobolev inequality with the following constant, provided it's finite. And that constant is just the sup of f divided by the inf of f times gamma. So provided this constant is finite, you basically get for free that any bounded perturbation of a measure for which you have already established, Log-Sobolev inequality also satisfies one. I'd like to comment on this this property, which is easy to check, but I'd like to comment on it briefly, because in the cases we're interested in, I mean, you could say start with a Gaussian measure. Let's check the Log-Sobolev inequality by the Bactriamri argument, and then try to apply this criterion to the perturbation, which is in our case e to the minus the potential v, for example. Now, if you try to do that, you see that you get constants which are exponentially bad in dimension or in epsilon and these parameters. You see the supremum and the infimum, they behave very badly with respect to scaling of dimension usually. So this is a sort of conceptually a good criterion and it's a good criterion and finite in a finite fixed number of dimension, but it's not terribly useful if you're in the case where you have a lot of dimensions. There's also you can there's the so-called Herbst argument or Gaussian concentration. So if nu, again, under the same assumption as before, satisfies the Log-Sobolev inequality with a constant gamma, then one has the and f is a one Lipschitz function. Then one can bound the one can get Gaussian moments for f. So you get what you would get for a Gaussian measure. And finally, I'd like to remark, there are many more consequences, but I'd like to remark one final useful property of the entropy, and which is that it has that it's given by a variational form, that it can be expressed in terms of variational formula, which is very useful. It's not something we'll use, but it's generally useful, so I'll mention it for background, which is that the relative entropy of mu with respect to nu can be written as the sup of E mu f minus log and in particular one obtains the so-called entropy inequality, which states that the expectation with respect to any measure mu of some observable f can be bounded in terms of well, the relative entropy of mu with respect to nu, this is supposed to be nu, plus an expectation with respect to nu. So there's So somehow if you control the relative entropy between two measures, you can reduce completely general expectations with respect to one measure to expectations with respect to the other measure. And that is very useful in, for example, hydrodynamic limits and so on. Okay, so much for some cultural background before we move on. Okay, so the next item I want to discuss is an example. And this example is something we've already seen in Nicolas' talk, basically. It's just the dynamics of a Gaussian free field. But I think it's instructive to just go through this again and see what the difficulty is. So in this case, the Hamiltonian h of phi is just quadratic. So it's just 1/2 phi, a phi, and a is a Laplacian. So let's say a is minus Laplacian plus, let's say, m squared or plus 1. And perhaps we can also put an epsilon here if we want. So let's say on the torus, and I usually prefer to regularize, put a little regularization in terms of a lattice n, but you don't need to in this case. Okay, so then the invariant measure is the Gaussian free field on the torus. And since it's a Gaussian measure and the dynamics is an Ornstein-Uhlenbeck process, which you can just diagonalize on Fourier basis. So the dynamics is diagonal. In Fourier basis. So if you look at the evolution of the Fourier modes of phi, so this k squared is only true exactly if you go to the limit epsilon to 0, but let's not worry about that. You can write this down like this, where these W hats are just independent Brownian motions in all Fourier modes. So this diagonalizes the dynamics in the Gaussian case, and something which we can just read off from this is that the different Fourier modes equilibrate at very different speeds. So the different Fourier modes which I think of as different length scales. So the small Fourier modes are large length scales and vice versa. So the Fourier modes correspond to length scales. They equilibrate at different rates. And what you see is, well, it equilibrates fastest, the faster the larger k is. So if k is very large, that corresponds to the small scales. Those equilibrate extremely quickly. While what's slowest are the large scales where k is of order 1, say. So the small scales so that is k is large. They converge very quickly. On the other hand, the macroscopic modes are the slowest ones. So this sort of describes in a very explicit way in this example of what's happening. You have this dynamics on these fields on the torus. These fields are in the continuum, if you like, but let's think of them as a discretized torus. Then you have the small rates and the small scales and the macroscopic ones. And really, you see a slow or movement at order 1 speeds for what's happening macroscopically. And all the smaller and smaller scales, the more you zoom in, the faster things move and the more irrelevant somehow those scales are. So here we can see this completely explicitly. Now, and quite generally, we expect a similar picture to be present in the interacting models that we'd like to study. It's just the difficulty is we cannot diagonalize these in Fourier space anymore, right? So the difficulty is the models we're interested in, remember they have Hamiltonian H, let's say of the form 1/2 phi a, possibly depending on epsilon phi, and then there is a potential, and the potential is a local potential, so it's a sum over points x of maybe some local potential little v of phi x, which is local and nonlinear. So it's nonlinear in real space, so that is it's non-local in Fourier space. So while we understand the quadratic part extremely well in Fourier space, it becomes diagonal there. Somehow the local part is competing with this. It becomes a mess in Fourier space. If you try to write this local part in the Fourier representation, it's a mess. Yet in many cases, so the principal problem that to deal with here to understand the relaxation of models like this is how do we deal with this competition of the local potential and the Laplacian term, which is nice in Fourier space. And so somehow we want to so in the Fourier space, we saw how the different length scales, you see how they move at different speeds, and we see this very explicitly. And we'd like to have a similar picture in the more general case, except that that Fourier analysis in this way is not immediately so useful there because of this potential term. Now, the approach that we follow is not to go through Fourier space, but it's rather to use the idea of renormalization as it comes from physics in the spirit of Wilson. And to explain this, I'd like to recall a few properties of Gaussian measures next. Okay. So let me maybe say this is Gaussian integration. So we start with the following setup. We consider a matrix CS. So this matrix as before is an n by n matrix, symmetric, positive, definite. And we assume it's given to us in the form of an integral from 0 to s or some other matrix, shall denote C dot of S prime, ds prime. And I'm also assuming that C dot is positive definite. So here positive definite is semi-definite for me, but in our application will actually be strictly positive definite. Okay, so and then we can look at the Gaussian measure P with that covariance CS. So let this be the Gaussian probability measure. With covariance CS. So the primary example that we'll be using is what I call the heat kernel decomposition. We just set C dot S to be e to the minus SA. So then C infinity becomes the integral of e to the minus SA, which is just A inverse. So the measure P C infinity is the Gaussian measure with covariance C infinity. The covariance C infinity being A inverse, A being the Laplacian. This is just the Gaussian free field in this case. If A is the Laplacian, let's say with a mass term or boundary conditions. So if A is, let's say, if is the Laplacian, then P C infinity is just the GFF on the torus, let's say. Okay, so this is the example I'd like to keep in mind, and we can define a Laplacian associated to these covariances. I'll denote this by Laplacian CS dot. It's given as follows: summing over all points xy. Remember, there's only finitely many of them. Then I'm taking this C dot matrix, and then I'm taking the second derivative to the direction phi x and phi y. Or written more concisely like this. So again, as before, let me just emphasize careful, these two Laplacians here, they have nothing to do with each other. I mean, nothing is maybe not quite true, but it's they're very different Laplacians, right? Two very different Laplacians. One is the Laplacian, say, on the lattice, and the other one is the Laplacian on R to the lattice, if you like. Okay, so this is the Laplacian associated to the covariance matrix, and in fact, it also has the following nice interpretation. If you define, so this Laplacian depends on S, right? So if you define a matrix GS inverse to be CS dot, or in other words, GS is CS dot inverse, then the Laplacian associated to this covariance I just defined is in fact nothing but the Laplace-Beltrami operator associated to this metric GS. So a little bit unfortunate notation, since the way I defined Laplacian with the index of a matrix is sort of the opposite as in the definition of the Laplace-Beltrami operator, where you see the inverse appearing. So this is the Laplace-Beltrami operator on R to the lambda associated to the metric GS. And so what is this metric GS? Well, remember GS is e to the plus SA, right? So remember CS, where's that? CS is e to the minus SA. So if we take the inverse, GS is e to the plus SA. So, and as we discussed before, you should think of A as a Laplacian. So e to the plus SA is something that may look a little bit frightening. It's a heat kernel with the wrong sign in the exponential. So a negative time heat kernel, if you want. But doesn't pose any problems for us. We've regularized everything. A is a matrix. We can take e to the plus or minus the exponential. It doesn't matter. And the interpretation is rather clear. So if we take a function, if we want to measure f, the norm, with respect to this metric of some f, so f is an element in R to the lambda. So f being in the unit ball of this metric, well, by definition, what does it mean? It means, well, it means that e to the plus SA over 2 f is in the L2 norm bounded by 1. So, but what does that mean? Well, it means that f is given by e to the minus SA over 2 of some f naught, where f naught is a function with L2 norm less than 1. Right, that's what it means, right? If you have some f which is given by e to the minus SA over 2 applied to f naught, then we can apply e to the plus SA to f and get a function of norm 1. So it means, and this here we have the heat kernel with the right sign. So what it means is that the unit ball in this metric just consists of all functions that are smooth at scale S. We think of a function to be smooth at scale S if it arises from some function which has unit norm and L2 norm, and then apply a heat kernel up to time S. That is a notion of smoothness up to scale S. The heat kernel up to time S, smoothest up to that length scale. More precisely square root S, but never mind for now. So the unit ball, of that metric.
Chat, Roland. So,
yeah.
So what is the T in the heat kernel?
The what? Oh, there's no T. This is a plus.
Oh, okay, yeah.
I mean, I didn't have to write a plus. I just want to put a plus here because this is not what you expect. Or
yeah.
It's the heat kernel with the wrong sign, but it's exactly what it should be. So the unit ball in this metric consists of functions smooth at scale, let's say square root S. The square root is what's appropriate if A is really Laplacian. Okay, so so this is just a little side remark, but it's an interpretation that might be useful to keep in mind. Okay, so okay, let me return to, okay, I can write this here, to the first property we need, which is that if we take the Gaussian measure with covariance CS, well, it satisfies a heat equation with this Laplacian. So, well, this is nothing but more general version of the fact that you know very well, which is that the fundamental solution to the heat equation is given by a Gaussian kernel. This is the multidimensional version of this, and here our heat equation is allowed to have coefficients depending on time, or so you may think of S as a time, but I will refer to it as scale. So okay, so this so let's check this proposition. Okay, so maybe I should recall that the Laplacian CS dot is the sum for x and y of C dot S x y. Okay.
So Roland, this reminds me a little bit of something people in PE calls the parametrics method. I don't know if it's related or not to this thing.
I don't, as far as I understand, I mean, not that I'm aware, but I'd be happy to learn more. Maybe we can discuss this after the end of the lecture, maybe.
Okay, it could be.
Okay. Okay. So let's just check this. So this is we just need to plug in definitions. So we want to plug in the definition of PCS. Well, PCS by definition is the Gaussian measure with covariance CS. So it's given like this. It's e to the minus a half phi CS inverse phi, and then there's a normalization constant. Okay, so we do this derivative. So okay, what happens? So if we differentiate S, well, we reproduce the exponential factor, and then we get the derivative of what's in the exponent. And in the exponent, we just have a quadratic form involving CS inverse. So the CS inverse becomes CS to the minus 2. So we write this as 1/2 CS inverse phi CS inverse phi. And then there's also, so maybe I should have, I'm using this notation with the inner product CS dot to denote, basically you take the two arguments and you put the CS dot in the middle. Okay, so this is coming from differentiating the exponential. And then we also get a term from differentiating the normalization constant, and that's just some constant multiplied by the measure itself. Okay.
Roland, so your formula looks a little bit awkward, the one that for the CS dot. There are some dots and minuses, one is missing, or...
Oh, sorry. Thank you. Good. I think this should be okay now. All right. And maybe I'll also write this as CS inverse phi CS dot squared. So this is the square with respect to this inner product involving CS dot.
I'm also doubt about the 1/2, but it's not.
You're doubting the 1/2. Indeed. You're probably right. The 1/2 shouldn't be there. Thank you. Okay, very good. Okay, let's differentiate the other term. So this is computing the left-hand side here, this one. Let's compute the right-hand side as well. So for the right-hand side, we compute Laplacian CS dot applied to PCS phi. So what is that? Well, in this case, so we differentiate with respect to phi. We get the following terms. We should be getting the same. Let me see if that is what happens. Right, in this case, so we differentiate. So let me write down what we should get. So we should get 1/2 CS inverse phi okay, so what did we do? So we're differentiating with respect to phi twice, right? There's two derivatives with respect to phi. So we how can that happen? Well, we take the exponential, we differentiate the exponential once. That brings down a CS inverse phi. In this case, I guess the 1/2 got canceled, and we've put it back here. Then we differentiate with respect to phi again. So now what happened is, well, what we can differentiate the term that's already been differentiated once, but that's already linear in phi, so it just contributes a constant here, multiplied by the measure. And then we can bring down another term from the exponential, which is giving us another CS inverse phi, and that would be this term. So I think got a little bit confused about the 1/2 here, but this seems to me is what we get. Okay, so comparing the two equations, we see that there's a problem with the factor 1/2, which I've gotten a bit confused about here, but it should be correct. So anyway, let's not worry about the factor 1/2, and notice that
I think the 1/2 that I told you shouldn't go, should go.
Sorry?
I think the 1/2 I told you it didn't
Yeah, I
go.
think so too. So I think you got me confused there.
Yeah, sorry about that.
Let's see.
Yeah,
Yes,
because
there's a 1/2.
Yeah.
Yes. Thank you. It's just we didn't differentiate the field phi, but we differentiated the covariance, right? So and that doesn't change the 1/2. Okay, so good. So we see that these two expressions are, let's put the 1/2 here too, so that we can compare them. That this is just a constant times PCS of phi. But that constant actually has to be 0. Well, why is that? Well, we can integrate both sides. And what happens if we integrate both sides? Well, on the left-hand side, we get 0. And so the right-hand side has to be 0 as well. Why is the left-hand side 0? Well, PCS is a probability measure. So if we integrate with phi, then the S derivative is surely 0. And the Laplacian term is also 0 because we're integrating a derivative and of a function that decays at infinity. So the integral of both sides of the left-hand side is 0. Okay, so the right-hand side, so we've checked this heat equation for the Gaussian measure. Good. I suppose my time is about up at this point, right?
Yeah.
Which is fine with me, because this is actually a very good point to stop. Next time we'll develop a few more properties of Gaussian measures, and we'll see how they blend in very nicely with the theory of Log-Sobolev inequalities in a bit. Okay.
Very good. So how is the protocol? I should unmute everyone and.
Yeah, I think we unmute everybody to applaud. Wait, I'm not sure actually how do I do that? Okay.
Yeah. Okay. Let me see. Yeah, and now, well, if
so there's
the
another
audience has some
here.
other questions, yes. So let's see if.
Let's see. There's some minus and plus sign.
Yeah, those are okay. No,
those are resolved. Okay. Well.
Yeah.
Yeah. Good.
So in that case, we resume. What time do we resume now? It's.
That's a good question that I can answer you once I've looked at the schedule. Wait. Right. So Nicolas' talk is at 3, so that's actually basically now in 15 minutes.
Oh, I see.
So 3 UK, 4 Germany. I don't know when Brazil. That's too complicated for me.
So there's a question here.
Yeah, can we interpret the derivative of the covariance matrix as a change of time for a Brownian motion? I mean, it's rather a change of the diffusion matrix somehow. I mean, you should think of maybe C dot as the diffusion matrix of a Brownian motion. So if you integrate, I mean, okay, if you take a Brownian motion with diffusion matrix C as dot, time S dependent, then that is basically equivalent to this change of the Gaussian measure. I think that's probably what your question meant. Does the Log-Sobolev inequality tell you anything about decay of correlations? It's not the, I mean, so in the cases that I'll present, we'll know everything about decay of correlations. That is a much easier question than the Log-Sobolev inequality in our case. I mean, by decay of correlation, I think what you mean is like endpoint correlation functions in equilibrium, which how they depend on space. And yes, there are criteria relating decay of correlations and general setups to Log-Sobolev inequalities on, let's say, on certain domains, but it's not what we. It's not our point. It's not what we have in mind. I mean, you can relate them to them, but it's okay.
Very good. Okay.
Okay. Another question. Is the modified Log-Sobolev inequality? Probably it is, but we don't care because we have the Log-Sobolev inequality. Anyway, this is continuous time, so they're equivalent anyway.
Yeah.
And spectral gap and other consequences you mentioned. Well, I mean, this is continuous time, so the modified Log-Sobolev inequality is the same as the Log-Sobolev inequality, right? So it's just, we even saw that here. Great. I mean, that's the same. Another question.
Is it possible to tell constant?
In the case of the double, well, it depends a lot on what you, so the question is, let me read it. Is it possible to obtain constant uniform in dimension for LSI in the case of the double well potential? So in general, no, because this model has a phase transition and it's just false. You can check at low temperature, it's not true, right? It's more subtle than that. Okay, that's, I mean, so what our goal here is to get Log-Sobolev inequalities with sort of optimal or the correct scaling and dimension and parameters for measures which have strong correlations, like behave like a free field at small or large distances. That's
very good. So maybe we can just stop because we are going to need to start very soon with Nicolas. So let me unmute everyone. Okay, everybody is unmuted, so we can clap again and thank Roland for this talk.